So, in this chapter, there are 4 sections, but our discussion will focus on section 4. But now what I will do is I will present on the whiteboard. Okay, so I will present the material on the whiteboard so that you can understand the line of thoughts. So here, first of all, we want to consider physics. Okay, so physics. Of course, many of you will need to take physics 1 and 2. In physics 1, the major considerations we need to have is about, say, forces and motion. Okay? We need to define motion, we need to define forces, and we need to study the connection between them. Okay? So here I'm using a basic language to tell you the idea behind physics. So especially physics 1. Okay? So physics 1, we study the physics of forces, motion, and the connection between forces and motion. And how do we succeed in learning physics? That's many people may be interested in this. To succeed in learning physics, in my perspective, we need to develop the so-called senses of geometry. Okay? Senses of geometry. Here are senses. So you may wonder what I meant by this. Geometry, you understand this very well. Okay? Most of you have learned geometry in high school. But what I meant by senses of geometry, it has 2 parts. One I would call it a speakable part. And the other part, I would call it an unspeakable part. Okay? And this sounds abstract, but we'll see the meaning very soon. Like this week, you will see what I meant by speakable and unspeakable. Speakable means it can be written in words. Like any description you see in a textbook or anything you find online. Okay, so any any online tutorials in physics about physics, those are speakable parts. But there will always be some unspeakable parts which you need to get those by yourself. Okay? So that means you need to, for example, through problem solving, you will get some insights, and those insights are what I meant by unspeakable part of those senses of geometry. So that means geometry is highly important for learning physics, because especially, so for example, motion is highly relevant to geometry, and forces, as we will see very soon this week, is also highly relevant to geometry. Okay? So some of you may have confidence, say, in calculus, okay, for example, and other math topics or subjects, but the key to success in this course, usually, okay, for most people, to develop senses of geometry is highly important. Okay? So, and we'll see what we meant by this very soon. So now let's move on. So now, since geometry is so important, we start with vectors, chapter 3. And first, I'm sorry. Yeah, this is not my computer, so that's why. Okay, so first we consider coordinate systems. And there are 2 kinds of coordinate systems we will learn this semester. One is called Cartesian coordinate system, which you have learned in high school. And the other is called polar coordinate system, which some of you may have heard it, but some of you may not have heard it, but it's fine. We will learn about all these things. So next page. So at this point, we are going to consider 2 kinds of quantities. One is called a scalar quantity. The other is called a vector quantity. Scalar quantity is when you see a scalar quantity, that can consist of, say, a value, a number, and in addition to that number, it also has some appropriate unit. Right? For example, if you consider the temperature, say, the temperature for today, let's say it's like a 55 Fahrenheit, for example, right? So then this kind of physical quantity we call temperature is a scalar quantity. Okay? Let's say temperature, we call it T, right? Say 55 Fahrenheit. So this quantity, physical quantity, is called a scalar quantity. It only consists of a number and a unit. Right? So that's called scalar quantity. But very soon we'll see another type of quantity which is called a vector quantity. It not only consists of a value and unit, but it also would have a direction. Right? So the vector quantity has a magnitude and direction, but scalar quantity has only a value and a unit. Right? So, but we'll see that very soon, what we mean by a vector quantity. A vector quantity here, let me move on to other pages. So here you have seen a vector here. Right? So a vector here, but vector is usually defined, can be represented by an arrow. Okay, by an arrow here. Here you have seen an arrow, but you have seen multiple arrows here. What they mean is as follows. When you define a vector, say I define a vector here. Okay, suppose I define a vector here, and now I would like to make this vector well defined. So I claim that if I parallelly shift this vector to another location in space, it will still be the same vector as long as it preserves its magnitude and direction. Okay? So I say here I have a vector here. It has a magnitude and direction, and it's represented by an arrow. But now if I try to parallelly shift this vector to another location, we will claim that it's still the same vector as long as its magnitude and directions are both preserved, right? And so that similarly, if we move this vector to yet another location, and it's still the same vector, as long as the direction and magnitudes are the same, right, as before, and so on. So that means vector, we have a unique representation, but actually, all these four things are actually the same vector, right? As long as the magnitude and direction are both preserved. So now let's move on. Okay, so now we move on to other things. So now, here, look at this part here. Okay? So currently we're still in chapter 3, but I presented the materials which are important and relevant to the test questions. Right? So I mean the principles that are relevant to test questions. That's why because for this course our time is limited, so that's why we can only present the materials that are most relevant for you to solve the problems. So now let's consider how do we add up two vectors. Okay? How do we add up two vectors? Let's consider a method here. The method of vector additions, there are two basic ways of adding up vectors. Suppose now I have two vectors. Okay? Says I have vector A, and vector A is usually denoted by this. Okay? I think many of you probably have seen this in high school. In high school, you may define a vector in terms of its components, like this. Say A is equal to like AX, comma AY, like this, right? And you have another vector B, which is written as BX, comma BY here, right? But very soon in this lecture, we are going to tell you a different way of representing vectors. But before we tell you the different ways of representing vectors, we would like to tell you how to get the sum of two vectors, for example. How would you get the sum of two vectors? So one method we can use is called the graphical method, and the other method we can use is called so-called analytical method. But there are actually two kinds of graphical methods. One kind is over here. So now we are in chapter 3. Okay? Chapter 3, we talk about this as a whole. So now this topic we are going to consider here is called vector addition. How do we add up two vectors or multiple vectors? So now we are going to add up. Say we have a vector A and vector B. We want to get the sum. So the sum of the two vectors, we call it R, equals A plus B, right? How do we get the sum? So there is a graphical method, and there's also analytical method. Okay. So graphical. So now this is the graphical method. But the first graphical method we are going to present to you is called the tip-to-tail method. Okay, so this one is called the tip-to-tail method. So to add up the two vectors, what you need to do is first, You consider the first vector A here. Then you connect the tip of vector A to the tail of your vector B. Connect them like this, right? So you have A and B. And then the last step is you connect from the tail of vector A all the way to the tip of vector B. So then this method is called the the tip-to-tail method of vector addition. So tip-to-tail method is just one of the two graphical methods we will tell you this semester. Okay? So tip-to-tail method is the first graphical method. But very soon we'll tell you another graphical method soon. Okay? So this is called tip-to-tail method of vector addition. Now let's move on. And this is some generalization. When you have 4 vectors, A, B, C, and D, how would you add them up? You connect the tip of vector A to the tail of vector B, and then connect the tip of vector B to the tail of vector C. Then you connect the tip of vector C to the tail of vector D. Then in the end, you connect from the tail of vector A all the way to the tip of vector D. So then this R is your resultant vector. So now you can somehow sense what I meant by the so-called senses of geometry. When you learn about physics, like in this chapter here, vectors, you do have some pictures in mind, like this, right? You don't just memorize equations, but you have some pictures in mind so that you know what's the geometrical meaning of such a description here. Right? So this is called tip-to-tail method here. Now let's move on. Oh. Sorry. Yeah. So there are some rules about vector addition, but that's not our main point here. Let's move to. Now let's move on to this subtopic here, analytical method. So there's another graphical method we'll see later, right? But now let's move on to the second method for adding up vectors, which is called analytical method for vector addition. So analytical method is presented here. So suppose you have 2 vectors, A and B, I wrote down here. So the title is here. I didn't write down a title, but you can write down a title, analytical method for vector addition. And how about if I want to add up 2 vectors A and B, so then I need to add up these 2 vectors component-wisely. So that means if there's a resultant vector R like this, right, and R equals A plus B, then what I will do is add them up component-wisely. So this will become AX plus BX, comma, AY plus BY. All right, okay, so you have the 2 components. But now what I need to tell you is, in this course, we are using a different notation. So those are high school notation, but now we are going to use this notation. We are going to represent this A as AX times I hat plus AY times J hat. And this vector B here, we're going to represent it as BX times I hat plus BY times J hat. Okay? So we have these 2 vectors, and what's the meaning of such kind of decomposition of vectors? Say, I write A as this, B as this. What did I really mean? So here, what I meant is as follows. Here you can define a coordinate system. Here this is X and Y. This is high school, okay? High school information, X and Y, and this is my origin. So now suppose I have 2 vectors, and suppose I have a vector A, which is somewhere, okay, so let's say vector A somewhere here, for example. And how do I represent my vector A? I'm going to represent my vector A by 2 unit vectors. So unit vectors I hat is defined as 1, 0. And unit vector hat is defined as 0, 1. Okay? Those are called unit vectors. Right? So like unit vector I hat is here, J hat is here. They are called unit vectors because their lengths are 1. Say if you consider the magnitude of I hat It's going to be equal to square root of 1 square plus 0 square is 1. Magnitude, okay? And magnitude of j hat is square root of 0 square plus 1 square, it's also 1. That's why those are called unit vectors. In geometry, now let's come to the senses of geometry. What's the meaning of that equation there? This equation there, here. Now, that means that A has two components. What you do is as follows. What did I mean by AX times I hat plus AY times J hat? You start with the unit vector I hat, then you rescale it by a factor of AX. So I hat is here. Rescale it, it will become this one. So this is I hat, right? I hat is the shorter one. And once you rescale it, it becomes this one. AX times I hat. Right? AX times I hat is this one. And now, this is J hat, right? And you rescale it by a factor of AY. Right? So here, let me draw it again. Okay? This was A, and this was I hat. So they rescale it, it becomes this one. AX times I hat. And this is J hat. We rescale it, it will become this. And after rescaling, it's called AY times J hat. And now you wonder, what's the meaning of AX times I hat plus AY times J hat? What do we mean by that, right? So what we mean by this is do the vector sum. When you do the vector sum, you consider the following. It's a bit weird, right? Because one vector is here. The other is here. How do I do the sum? They are in two totally different directions, right? They are perpendicular to each other. You have this, okay, this vector which points toward the right, and this vector which points straight up, right? And how would you do the sum? Once you do the sum, it's here to describe this direction, right? So and this is I meant by senses of geometry. Geometrically, you consider vector addition as this. When you have two vectors, you consider these two vectors as two adjacent sides, okay, of a parallelogram. And so here is actually a rectangle, because rectangle is a special case of a parallelogram since they are perpendicular. This vector, okay, AX I hat and AY J hat, those are two adjacent sides of a parallelogram. The first thing you do is you can complete the parallelogram like this. But here, of course, it's a rectangle, right? Complete the parallelogram like this. Use a virtual dashed line to complete a parallelogram. Then you try to draw a diagonal vector from their common vertex here, all the way to the opposite vertex of that rectangle, and that will give you your vector A. Right? So that's what we mean by vector addition. So vector addition, this is the so-called analytical method. You write down each vector in terms of components, and then you will be able to do the sum component-wisely, right? But geometrically, how would you represent those components? So AX times I hat is this, AY times J hat is this, and then when you do the vector sum, consider the geometry, which is consider these two vectors as two adjacent sides of a parallelogram. In this case, it's a rectangle. And then you connect from the common vertex all the way to the opposite vertex and draw an arrow, and that arrow is your vector A. That's what we meant by getting the sum of AX I hat plus AY J hat. Since AX I hat and AY J hat, they are always perpendicular to each other, so you cannot mix those two components. So when you do the sum, how would you do the sum? Let me erase this, okay? Because this part, older pair was the high school notation. But now we are in college, so we are using the I hat and J hat notation, so it will become this one. AX plus BX times I hat plus AY plus BY times J hat. All right? Okay, so that's how we do the sum of two vectors. We get the sum component-wisely. AX sum up with BX and times I hat. AY sum up with BY times J hat. But we cannot mix the two components because physically, AX I hat and AY J hat, they are perpendicular to each other, right? So the sense of geometry tell you that the vector A points in the diagonal direction. Okay? So that's what we meant by the senses of geometry here. So now let's move on very quickly here. So in the textbook, when you read, you will see the procedure. So again, those are speakable part. The procedure is speakable, but you need to connect the procedure to the geometry. Okay? So that's the unspeakable part of the senses of geometry. So now let's look at here. How would you get the sum? You have vector A, right? Vector B, and then you use the tip-to-tail method, for example, right? Tip-to-tail method, connect the tip of vector A to the tail of vector B. Then eventually you connect the tail of vector A all the way to the tip of vector B. Then you get the resultant vector. Okay? That's what we meant by here. So the resultant vector also has two components. Let's consider this here. The resultant vector has two components. This part, we can call it Rx. This part, we can call it Ry. Okay? Those are the two components of that resultant vector. Okay? So in Rx equals what? Ax plus Bx. Ry equals Ay plus By. Right? So after this lecture, we will discuss about some practice questions. So I will post those practice questions after the lecture. Right? There are 4 questions there, but in class I can only present probably 2 of the 4 questions here. Right? So that's the basic idea of chapter 3. Chapter 3, but we haven't finished yet. Okay? So in the lecture on Friday, I will finish chapter 3 and move on to section 4.6 to talk about so-called relative velocity. Okay? Relative velocity. So anyway, so thank you all. Hope you all have a great day. See you again next time on Friday. Okay?